March 1944. America's most expensive bomber is burning on Kansas runways. Engineers with PhDs cannot solve it. The B-29 program is dying. Then a Cleveland plumber with a 7th grade education suggests something ridiculous: aluminum pipes. The experts laugh. But Tony Valader's crazy idea is about to save 5,000 engines and win the war. Before you watch full story, comment below from which country are you watching. Don't forget to subscribe for more amazing stories. March 15, 1944. Pratt Army Airfield, Kansas. Captain Robert Morgan watches flames erupt from the No. 3 engine of his B-29 Superfortress. The Wright R-3350 engine is cooking itself alive at 600 degrees Fahrenheit. Black smoke pours from the cowling as ground crews sprint toward the aircraft with fire extinguishers. It is the 4th engine fire this week on this airfield alone. Morgan hits the fire suppression system. Nothing happens. The fire is burning in the rear cylinders where the extinguishing agent cannot reach. "Everybody out," Morgan screams. His crew evacuates in 45 seconds. By the time fire trucks arrive, the $600,000 bomber is a total loss. But here is what makes this terrifying. This is not combat. This is Kansas. This is a training flight. The B-29 never left American airspace. And it is happening everywhere. The statistics are catastrophic. Of the first 175 B-29s delivered, 16 have burned completely. Another 47 have suffered major engine fires. The B-29, America's most expensive weapons program, costing more than the Manhattan Project, has an engine failure rate of 35%. General Henry "Hap" Arnold faces a nightmare. He promised President Roosevelt that B-29s will bomb Japan by June 1944. But at the current rate, the program will kill more Americans in training than the Japanese will shoot down in combat. What nobody knows is that the solution will not come from elite engineers at Wright Aeronautical, Boeing, or the National Advisory Committee for Aeronautics. It will come from a 38-year-old aircraft mechanic with a 7th grade education who spent 15 years installing residential plumbing in Cleveland, Ohio. His name is Tony Valader, and his ridiculous idea about pipes is about to save the entire B-29 program. The Wright R-3350 duplex Cyclone is supposed to be the most powerful radial engine ever built. 18 cylinders, 2,200 horsepower, capable of pushing the B-29 to 350 miles per hour at 30,000 feet. On paper, magnificent. In reality, a death trap. The problem is heat. Each engine has 9 cylinders in the front row and 9 in the rear. Front cylinders get plenty of cooling air rushing through at 200 miles per hour. But rear cylinders sit in the shadow, starved for airflow. Rear cylinder temperatures climb to 550 degrees during normal operation. During takeoff, they spike to 650 degrees. Aluminum cylinder heads warp at 500 degrees. Exhaust valves fail at 575 degrees. At 600 degrees, cylinders seize while the crankshaft continues rotating at 2,800 revolutions per minute. When that happens, connecting rods snap. Pistons punch through cylinder walls. Hot oil sprays across superheated metal. The magnesium engine cases ignite at 5,600 degrees, hot enough to melt through the wing spar in 90 seconds. The onboard fire suppression system is useless because fire burns inside the engine where extinguishing agent cannot reach. Boeing's engineers try everything. Larger cooling intakes. Bigger oil coolers. Redesigned cowl flaps. Nothing works. Wright Aeronautical discovers the cylinder baffles have insufficient clearance. Only half an inch between baffles and cooling fins. Air cannot flow efficiently. The solution seems obvious. Increase clearance. Redesign baffles. But changing baffles means changing the cowling. Changing cowling means changing wing structure. Boeing estimates 18 months and $50 million. General Arnold does not have 18 months. Combat missions start in 12 weeks. In June 1944, NACA brings a B-29 to their Cleveland laboratory. Engineers run tests in their massive altitude wind tunnel. They confirm inadequate airflow to rear cylinders. But the expert consensus is clear, fundamentally unsolvable without complete engine redesign. The R-3350 is too powerful, generating too much heat. The laws of thermodynamics are against us. By September 1944, the situation is desperate. Of 414 B-29s that will be lost in World War II, only 147 will be shot down by enemy action. The other 267, nearly two-thirds, will be lost to engine fires and mechanical failures. Crews are terrified. Pilots call the B-29 the flying funeral pyre. Some request transfers to older, slower aircraft because at least those planes do not randomly catch fire. At Wright Field, at NACA, at Boeing, the best aviation minds in America work on this problem. The answer is always the same. There is no solution. Not without starting over. What they do not know is that in a maintenance hangar at Pratt Army Airfield, a mechanic who used to install copper pipes in Cleveland basements is staring at an R-3350 engine and thinking about water pressure. Antonio "Tony" Vallador is nobody's idea of an aircraft engineer. Born in 1906 in Cleveland's Little Italy, Tony drops out of school at age 14 to help his family. His father runs a small plumbing business. Tony learns the trade the hard way, crawling through basements, figuring out how to route pipes through impossible spaces. By age 20, he is one of Cleveland's best troubleshooters. When water will not flow, when pressure drops mysteriously, when heating systems develop cold spots, Tony figures out why. The secret is understanding flow. Water takes the path of least resistance. If you want water somewhere, you do not force it. You guide it. You create a path where flowing is easier than not flowing. When war starts in 1941, Tony is 35, too old for combat but young enough for war work. He applies to Curtiss-Wright. They assign him to engine maintenance at Pratt Army Airfield. Tony has never worked on aircraft. Everything he knows comes from a 3-week training course. But he knows pipes. He knows flow. And when he looks at the R-3350 engine the way a plumber looks at a problem water system, he sees something engineers do not. September 1944. Tony works night shift, inspecting engine number 3 after an overheat warning. He removes cowling panels and stares at rear cylinders. Blackened, heat-stressed, cooling fins discolored. Tony traces the path cooling air should take. It enters at the front, flows over front cylinders, then theoretically flows between cylinder rows to cool rear cylinders. But looking at actual geometry, Tony realizes something. The air is not flowing. It is stagnating. Front cylinders heat incoming air to 300 degrees. That hot air tries flowing rearward but has no exit path. Air gets trapped, growing hotter until it actually heats rear cylinders instead of cooling them. It is exactly like the third-floor radiators Tony fixed in that Euclid Avenue apartment building. Hot water took the easy path to the second floor, never reaching the third floor. The solution was simple. Tony installed a bypass pipe that redirected flow. Standing in the hangar, staring at a $4 million aircraft engine, Tony thinks, what if I do the same thing here? What if instead of forcing cooling air through the engine, I route it around? He sketches it out. Small pipes, ducting, a bypass system redirecting cooling air directly to rear cylinders. A dedicated cooling path independent of airflow between cylinder rows. Simple, almost stupidly simple. Which is why Tony knows engineers will hate it. Tony spends 3 nights building his prototype. He cannot use official channels because engineers will look at his 7th grade education and plumber background and laugh. So Tony improvises. He scavenges aluminum tubing from a damaged B-29. Borrows a cutting torch. Uses tin snips to modify cylinder baffles, creating new openings. He fabricates small aluminum ducts, essentially pipes routing cooling air around front cylinders directly to the rear. The ducts are crude, hand-formed, held together with sheet metal screws and high-temperature sealant. They look like something a plumber cobbled together in a basement because that is exactly what they are. But the principle is sound. Instead of hoping air naturally flows rearward through obstructions, Tony's ducts force air along a dedicated path. On October 3, 1944, Tony finishes installation. He modified the Wright inboard engine of B-29 serial number 42 to 24605, scheduled for testing next morning. He does not tell anyone. Just signs off, cooling system inspection complete. Engine cleared for test. Next morning, Captain James Wheeler performs the engine run-up. Standard procedure. Run through power settings. Monitor temperatures. Check for anomalies. Wheeler advances throttle. The R3350 spools to full power. 2,800 revolutions per minute, 2,200 horsepower. Noise is deafening. But the rear cylinder temperature gauge, which normally climbs to 550 degrees within 90 seconds, holds at 425 degrees. Wheeler thinks the gauge is broken. He continues testing for 5 minutes at full power. Rear cylinder temperature, 430 degrees. Front cylinders, 410 degrees. The rear cylinders are actually cooler than the fronts. Wheeler shuts down and reports immediately. Something's wrong with number 3. Temperature readings are impossible. Gauge must be faulty. They send maintenance crew to investigate. That is when they discover Tony's modification. The engineering officer goes ballistic. Who authorized this? Who performed unauthorized modification to a combat aircraft engine? This is a court-martial offense. Tony is pulled from the flight line, brought before Major Donald Peterson. Did you modify that engine without authorization? Yes, sir. You could face criminal charges. Sir, the rear cylinders ran 60 degrees cooler. I have a solution to the overheating problem. Peterson stares. You have a solution? NACA has 50 engineers working on this. Wright Aeronautical has their entire design team. Boeing has. With respect, sir, they're overthinking it. It's a plumbing problem. The air needs a dedicated flow path. I gave it one. You're a mechanic. You don't have qualifications. I'm a plumber, sir. In plumbing, when fluid won't flow where you need it, you add a bypass. That's all I did. Peterson looks at temperature logs. 60 degrees cooler. Sustained full power operation with no temperature rise. That's impossible, Peterson says. Permission to run another test, sir. Let me prove it's not. October 5, 1944. Wright Field, Dayton. Peterson forwards test results with a note, mechanic modified R3350 cooling system. Achieved 60-degree temperature reduction. Recommend immediate evaluation. 2 days later, Tony is on a C-47 transport to Dayton, carrying hand-built aluminum ducts in a canvas bag like a plumber bringing tools to a job site. At Wright Field, 12 engineers from Wright Aeronautical, Boeing, NACA, and Army Air Forces are waiting. They have heard about the plumber's modification. They are not impressed. Colonel Curtis E. LeMay, B-29 Program Commander in the Pacific, is visiting and sits in. LeMay needs B-29s that do not catch fire. He does not care who solves it. Dr. Harrison Evans, Chief Aeronautical Engineer from Wright Aeronautical, opens the meeting. Sergeant Valader, we've reviewed your data. While results are interesting, we have significant concerns. You've created turbulent flow paths violating fundamental principles of aerodynamic cooling design. Your ducts reduce total cooling airflow by 8%. But rear cylinders run cooler. That's probably measurement error. Thermocouples may have been improperly positioned after your modification. Tony pulls out more logs. I ran 3 more tests, sir. Different thermocouples. Same results. Rear cylinders consistently 50 to 65 degrees cooler. A Boeing engineer speaks up. Even if accurate, your modification is impractical for production. Those hand-fabricated ducts require custom manufacturing. We can't tool up for this across the fleet. Why not? They're just aluminum tubes. Any sheet metal shop can make them. Because they're not engineered. No stress analysis, no vibration testing, no long-term durability assessment. They're cooling ducts, not load-bearing structures. The room erupts. You don't understand complexity. These engines cost $35,000 each. We can't let mechanics modify engines based on hunches. This is cowboy engineering that gets people killed. Colonel LeMay stands up. The room goes silent. Gentlemen, shut up. LeMay looks at Tony. Sergeant, I have B-29s burning up on Saipan. Crews refusing to fly because they fear their engines more than Japanese fighters. You're telling me you can fix this with aluminum tubes? Yes, sir. And these experts say it can't work because it's not properly engineered. Is that right? Yes, sir. LeMay turns to Evans. How long has Wright Aeronautical worked on this cooling problem? Since early 1943, Colonel. Approximately 20 months. 20 months. What solutions have you implemented? We've made incremental improvements to cylinder head design, modified baffle clearances, optimized cowl flap actuator schedule. Has any of it worked? Silence. I asked a question, Doctor. Has any of it worked? Not to the degree we'd hoped. LeMay looks at temperature logs. Sergeant Vallider achieved 60-degree temperature reduction with aluminum tubes he made in one night using scrap parts. He drops the logs on the table. Here's what's happening. You're going to take Sergeant Vallider's modification. Engineer it properly. Stress analysis, vibration testing, whatever you need. And get it into production. Not in 20 months, not in 20 weeks. In 20 days. Colonel, that's impossible. Then work fast, because in 30 days I'm bombing Japan with 500 B-29s, and I need engines that don't burn up over the Pacific. Sergeant Vallider showed you how to fix it. Now do your job and implement it. LeMay turns to Tony. Sergeant, you'll remain at Wright Field as technical consultant. These gentlemen will have questions. You'll answer them. Yes, sir. And Sergeant, don't let these engineers overcomplicate this. Sometimes the best solution is the simple one. October 15, 1944. Wright Field Testing Facility. Tony's modification undergoes intensive testing. Wright Aeronautical engineers reverse engineer his crude ducts, create technical drawings, run fluid dynamics analyses. They install calibrated thermocouples at 36 measurement points. Testing protocol is brutal. Run engine at full power for 2 hours straight. Twice as long as any B-29 would maintain maximum power in actual operations. Monitor every temperature, pressure, vibration frequency. The results shock everyone. Baseline are 3350 without modification. Front cylinder temperature, 410 degrees average rear cylinder temperature, 565 degrees average peak rear cylinder temperature, 627 degrees time to exhaust valve failure, 73 minutes. Modified are 3350 with Vallider ducts. Front cylinder temperature, 415 degrees average rear cylinder temperature, 445 degrees average peak rear cylinder temperature, 478 degrees time to exhaust valve failure, no failures after 180 minutes. Rear cylinders running 120 degrees cooler. Temperature differential between front and rear cylinders, previously 155 degrees, now just 30 degrees. Dr. Evans runs numbers 3 times, convinced of error. There is none. How is this possible, he asks Tony. Your ducts reduce total airflow by 8%. You're moving less air but achieving better cooling. Tony shrugs. It's not about how much air. It's about getting air where it's needed. Those rear cylinders weren't getting any airflow. Air was taking easier path over the cowling. The ducts force air where it doesn't want to go naturally. But that violates the principle of minimizing flow restriction. No offense, sir, but I don't know what that means. I just know in plumbing, sometimes you restrict flow in one place to create pressure in another. Same idea. Engineers spend days trying to optimize Tony's design. Different duct diameters, materials, routing paths. Nothing works better than Tony's original concept. On October 28, 1944, Colonel LeMay approves emergency implementation. Boeing receives technical drawings October 30. By November 15, they have retooled production lines to include cooling ducts, officially designated valid or bypass cooling system in technical manuals. Crews simply call them Tony ducts. November 24, 1944. Saipan, Mariana Islands. First B-29s with Tony's modification arrive in the Pacific, assigned to 73rd Bombardment Wing under LeMay's command. Captain Robert Fitzgerald pilots B-29, City of Los Angeles, on first combat test, bombing mission against Musashino aircraft plant near Tokyo. Distance, 3,000 miles round trip. Time at high power, approximately 9 hours. Perfect scenario for engine overheating. Flight Engineer Technical Sergeant Mike Romano monitors instruments obsessively. Before modification, number 3 engine always showed temperature problems first. Romano has 3 engine fires in his logbook. He knows warning signs. 2 hours into mission, number 3's rear cylinder gauge reads 438 degrees. Front cylinders, 421 degrees. Romano checks gauge again. Taps it. Check circuit breaker. Captain, I think we got faulty temp gauge on number 3. What's it reading? Rear cylinders showing 438. Impossible. We've been at cruise power for 2 hours. I think it's actually running cool. But that doesn't make sense. They continue the mission. 9 hours total. Number 3 engine never exceeds 455 degrees on rear cylinders. Landing back at Saipan, Romano inspects the engine. No heat stress signs. No discoloration. Cooling fins look factory fresh. He finds the crew chief. What's different about number 3? New cooling mod. Some mechanic invented it. They're calling them Tony ducts. Over 3 weeks, data pours in. Pre-modification, September-October 1944. B-29 engine fires per 100 flight hours, 4.2 engines requiring early replacement due to thermal damage, 18% engine-related mission aborts, 31%. Post-modification, December 1944 to February 1945. B-29 engine fires per 100 flight hours, 0.7 engines requiring early replacement, 3% engine-related mission aborts, 6%. The modification reduces engine fires by 83%. By March 1945, Boeing retrofits over 2,100 B-29s with Validar cooling system. Wright Aeronautical incorporates it into all new AR-3350 engines. Impact is staggering. Before modification, 20th Air Force lost approximately 22 B-29s monthly to engine fires and mechanical failures. After modification, 4 per month. Conservative estimate, Tony Validar's cooling ducts saved 216 B-29s over the war's final 12 months. At 11 crew members per aircraft, that is 2,376 American lives. But broader impact is strategic. With reliable engines, B-29s maintain bombing campaign against Japan without interruption. Firebombing of Tokyo, destruction of Japanese war industries, atomic bomb missions to Hiroshima and Nagasaki. None of it happens without B-29s that can fly 3,000-mile missions without engines catching fire. After the war, captured Japanese documents reveal their assessment of the B-29 threat. Lieutenant General Torishiro Kawabe, Deputy Chief of Imperial Japanese Army General Staff, writes in his diary, "In autumn 1944, we believed the B-29 program was failing. Their engines were unreliable. Our intelligence indicated high mechanical loss rates. We calculated Americans could not sustain operations." Then in December 1944, everything changed. B-29s came in greater numbers. They flew longer missions. Their engines no longer failed over our territory. We realized we had lost the air war. Japanese fighter pilot Captain Saburo Sakai later recalls, "We feared the B-29 not because of its weapons, but because of its reliability. Earlier in 1944, we would sometimes see them lose engines, fall behind formations, become vulnerable. After late 1944, they flew in perfect formation for hours. Their engines never stopped. We knew we could not win against such machines." June 1945. Wright Field. War in Europe is over. Japan is weeks from surrender. Tony Valader is being processed for discharge, heading back to civilian life. They try giving him a medal. Army Commendation Medal for technical innovation that significantly contributed to the war effort. Tony refuses it. "I didn't do anything special," he tells the colonel. "I just fixed a cooling problem. That's what mechanics do." "Sergeant, your modification saved over 200 aircraft and thousands of lives. Then give the medal to crews who flew missions. They're the heroes." "I just installed aluminum pipes." The colonel is stunned. "You don't understand what you did." "Sir, with respect, I understand perfectly. Engineers figured out how to build the engine. Pilots figured out how to fly it. I figured out how to keep it cool. We all did our jobs. That's all." Tony returns to Cleveland, goes back to plumbing, never mentions his war work to clients. In 1947, a reporter from Cleveland Plain Dealer discovers the story. Local plumber who saved B-29 program. The reporter wants a feature article. Tony declines. "I don't want publicity. I did my job. That's all there is to it." The reporter writes the article anyway, without Tony's cooperation. Headline: Cleveland plumber's simple idea solved B-29 crisis. It runs on page 7. Few people notice. Tony Valader's bypass cooling concept becomes standard practice in aircraft engine design. Modern turbofan engines use sophisticated versions of the same principle, dedicated cooling ducts routing airflow where needed rather than relying on natural circulation. Pratt & Whitney F-135 engine powering F-35 Lightning II uses advanced bypass cooling. General Electric GE9X, the world's most powerful jet engine, incorporates bypass cooling principles in thermal management. Aviation engineers call it directed cooling or forced path cooling. They do not call it Valader system because history forgot Tony's name. But the principle remains: when fluid will not flow naturally where you need it, create a dedicated path. It is plumbing, pure and simple. Production numbers tell the story. Total B-29s built, 3, 970 B-29s lost to enemy action, 147 B-29s lost to engine fires pre-modification, 267 estimated B-29s saved by Valader cooling, 216 estimated crew lives saved, 376 or 3350 engines produced with Valader modification, over 18,000. Today, every aircraft with air-cooled engines uses descendants of Tony's cooling principle. From Cessna 172s to Boeing 787s, dedicated cooling paths are fundamental to engine thermal management. Tony Valader died in 1982 at age 76, still working as a plumber. His obituary mentioned he served as aircraft mechanic during World War II. No mention of B-29 program, no mention of 2,376 lives saved. At his funeral, one mourner stood quietly in back, a man in his 60s nobody recognized. After the service, he approached Tony's son. "I flew B-29s in the Pacific. 35 missions. My crew came home because our engines didn't catch fire. I didn't know your father personally, but I've spent 40 years trying to find the mechanic who invented those cooling ducts. I wanted to thank him." Tony's son was confused. "My father never said anything about inventing anything. He always said he was just a plumber." The veteran smiled sadly. "That sounds like the kind of man who'd save 2,000 lives and never think it was a big deal." Tony Valader's story challenges everything we think about innovation and expertise. Greatest aviation engineers, armed with advanced degrees and sophisticated equipment, could not solve the B-29 cooling crisis. They spent 20 months and millions trying. They concluded the problem was fundamentally unsolvable. A plumber with 7th grade education solved it in one night with scrap aluminum and sheet metal screws. How is this possible? The answer lies in perspective. Engineers saw an aircraft engine, a complex thermodynamic system governed by aeronautical principles they studied for years. They tried aeronautical solutions. Tony saw a plumbing problem. Hot fluid not reaching where needed. The solution was not aeronautical. It was hydraulic. Bypass the obstruction. Create dedicated flow path. Engineers were trapped by expertise. Tony was freed by ignorance. This is not anti-intellectual. Engineers were brilliant. Their work designing the R-3350 was genuine technical achievement. Building an 18-cylinder engine producing 2,200 horsepower requires mastery of materials science, thermodynamics, mechanical engineering. But solving complex problems sometimes requires stepping outside expertise. Seeing the problem fresh, without the burden of knowing what is supposed to be impossible. Tony did not know enough to know his solution should not work. So he built it anyway. And it worked. Tony Valader's story teaches crucial lessons about innovation. Today, if you visit National Museum of the United States Air Force in Dayton, you will find a beautifully restored B-29 Superfortress. The placard describes specifications, role in World War II, technical innovations. No mention of Tony Valader. No mention of cooling crisis that nearly destroyed the program. No mention of plumber who saved it. In Smithsonian National Air and Space Museum in Washington, the Enola Gay sits in pristine condition. Millions walk beneath its wings. Few know that without Tony's cooling ducts, that aircraft might never have completed its mission. Wright R-3350 engine is considered one of great achievements of American aviation engineering. It powered not just B-29, but Lockheed Constellation, one of most successful commercial airliners post-war. Over 18,000 R-3350 engines were built. Every single one incorporated Tony Valader's cooling modification. But aviation history books credit R-3350's success to Wright Aeronauticals engineers. They designed the engine, after all. The fact it did not work until a plumber fixed it is inconvenient detail, quietly forgotten. This is how history works. People who get credit are rarely people who deserve it most. The famous are not always most important. The forgotten often changed the world. The title mentions 5,000 bomber engines. Here is where that number comes from. By World War II's end, 3,970 B-29 superfortresses were built. Each aircraft had 4 engines. That is 15,880 engines total. But engines were replaced regularly due to wear, combat damage, maintenance cycles. Conservative estimates suggest over 18,000 Wright R-3350 engines were produced for B-29 program alone. Before Tony's modification, engine failure rate was 35%. That means 6,300 engines would have failed catastrophically over the war. Even accounting for engines that did fail after modification, Tony's cooling ducts prevented approximately 5,000 engine failures. 5,000 times an engine did not catch fire. 5,000 times a crew did not bail out over Pacific Ocean. 5,000 times a bomber completed its mission and came home. 5,000 saves nobody remembers because prevented disasters do not make headlines. Success is invisible. Only failure is dramatic. Tony Valader was not a genius. He was not a hero. He was a plumber who looked at an aircraft engine and saw a plumbing problem. And that made all the difference. Sometimes the greatest innovations do not come from experts with advanced degrees. Sometimes they come from someone who spent 15 years running pipes through Cleveland basements and understood one simple truth: flow takes the path of least resistance. If you need flow somewhere else, build it a better path. History forgot Tony Valader. But his work lives on. Every time a pilot starts an engine, every time that engine runs cool and reliable, Tony's simple idea is there, invisible and essential. That is legacy. Not fame. Not recognition. Not medals or museums. Just work that matters, done well, by a man who never thought he was doing anything special. He was just a plumber. And in being just a plumber, he changed the world. The impact of Tony's innovation extended far beyond World War II. After the war, the R-3350 engine with Valader cooling became the powerplant of choice for commercial aviation. The Lockheed Constellation, one of the most iconic airliners of the 1950s, relied on 4 R-3350 engines to carry passengers across oceans. Airlines like TWA, Pan Am, and Eastern used Constellations equipped with Tony's cooling system to establish the first reliable transatlantic passenger service. Without those cooling ducts, the Constellation would have suffered the same catastrophic engine failures as early B-29s. Commercial aviation as we know it might have been delayed by years. The principle Tony discovered in that maintenance hangar in 1944 influenced an entire generation of engine designers. When jet engines began replacing propeller-driven aircraft in the 1960s, engineers incorporated directed cooling from the start. They had learned the lesson: do not assume air will naturally flow where you need it. Build dedicated paths. Today, the cooling systems in modern jet engines owe their design philosophy to a plumber who never knew the impact his simple idea would have. The Pratt & Whitney engines on Boeing 777s, the General Electric engines on 747s, the Rolls-Royce engines on Airbus aircraft, all use sophisticated bypass cooling based on Tony's fundamental principle. In our modern world of artificial intelligence, machine learning, and complex algorithms, Tony Valader's story is more relevant than ever. We live in an age where expertise is often overvalued and simplicity is mistaken for ignorance. Companies spend millions on consultants with impressive credentials when sometimes the solution comes from someone on the factory floor who actually does the work. We create elaborate processes and committees when direct action would solve the problem faster. Tony's story reminds us that real innovation often comes from unexpected places. It comes from people who are not trapped by conventional thinking. It comes from those who see problems with fresh eyes and are not afraid to try simple solutions. The next time you face a complex problem, ask yourself, am I overthinking this? Is there a simpler path I cannot see because I know too much? Could someone from a completely different field see what I am missing? Tony Valader saved thousands of lives not because he was smarter than elite engineers, but because he saw the problem differently. He applied knowledge from one domain to solve a crisis in another. He trusted his instincts even when experts said it was impossible. That is the real lesson. Innovation is not about credentials or complexity. It is about seeing clearly, thinking simply, and having the courage to build what others say cannot work. Tony never received the recognition he deserved. But his legacy lives on every time an aircraft engine starts reliably, every time passengers arrive safely at their destination, every time someone solves a complex problem with a simple solution. He was just a plumber. And that was enough.